Here paging concept is nothing but a paging is nothing but it is a memory management scheme. A paging is nothing but it is a memory management scheme that permits the physical address space of a process to be in non-contiguous. So paging is a which method? Non-contiguous method. Paging is a memory management scheme that permits the physical address space of a process to be non-contiguous manner. So by using paging concept, we have how to avoid the external fragmentation. By using the paging concept, we have to avoid the external fragmentation. So, in previous class, we discussed the external fragmentation is nothing but it will be memory existing. It is a non-contiguous. There are free memory is there. It is stored in non-contiguous locations, but it is a not contiguous. So for that, we have to remove that external fragmentation. Paging is used. So it avoids the external fragmentation by using paging concept, and it is a need for compaction. Compaction is nothing but it will be collect the free memory space in a large memory. It can be connected in a free memory space, a small free memory space, and it will be doing as a large free memory space. That is the compaction. So it also solves the considerable problem of fitting memory chunks. Memory chunks means free memory spaces of varying sizes onto the backing store. So this is the introduction about paging. So paging is nothing but it is a memory management scheme that permits the physical address space of a process to be a non-contiguous. So by using paging concept, we have to avoid fragmentation, that is external fragmentation, but there is a need for compaction. So what is the paging here? A physical memory. So there are two memories there. One is physical memory, another one is logic memory. That is a basic method of paging. So a physical memory can be divided into fixed size blocks. A physical memory can be divided into fixed size blocks called as frames. Here the size is power of 2. Here the size is power of 2 means, for example, 2 power 8 means 512 bytes. That is the range, that is the size of power of 2. So divide the physical memory into fixed size blocks called as frames. Whereas coming to the pages, what is the page? So page is nothing but logical memory is divided into blocks of same size. Logical memory is divided into blocks of same size called as pages. Very, very important definition. What is a frame and what is a page? So physical memory is divided into pages. So frame and pages. So physical memory into fixed size blocks called frames. Logical memory divided into blocks of same size called as pages. So page address is nothing but logical address. The page address is nothing but logical address. It is represented by page number and plus page offset. What is the page address? Page address is nothing but it is same as logical address, and the logical address is represented by page number plus page offset. How to represent the physical address? So frame address is nothing but physical address. So physical address is represented by frame frame number plus page offset, not frame offset. Frame number plus page offset. So that is a basic concept. You have basic method for paging. So here every address is generated by the CPU. So here every address is generated by the CPU. See here, address translation scheme, how the address can be calculated, and it will be send this data from CPU to a physical memory, that is main memory here. So every address is generated by the CPU. So every address is generated by the CPU is divided into two parts. One is page number, another one is page offset. One is page number, another one is page offset. I already told you logical address is nothing but page number plus page offset. Logical address is nothing but here P is nothing but page number and D is nothing but offset. Whereas physical address is nothing but frame number plus offset. Here F is nothing but frame number and D is nothing but offset. So here every address is generated by the CPU is divided into two types, that is one is page number and another one is page offset. So page number, what it will be indicates the page number, it is used as an index. So page number is nothing but it is used an index into the page table. So there is a page table here. So this is the page number. Page number is represented as index into the page table. That is the page number. So page number is used as an index into page table which contains the base address. It will be stored into the physical memory. So each page is must and should be stored into the physical memory. Next, page offset. So page offset, I already told you, page offset is represented by D, small d. So by using page offset here, combined with the base address, combined with the base address to define the physical memory address. So that is the page offset combined with the base address to define the physical memory that is sent to the memory unit. See here, that is sent to the memory unit combined with base address to define with the physical memory address that is sent to the memory unit. So this is the address translation scheme. Address is generated by the CPU is divided into page number and page offset. So here page number is higher order bits, that is m minus n bits of logical address. So page number is nothing but here page size is an higher order bits, page number is nothing but higher order bits, that is m minus n bits of logical address, where the page number indicates the logical address. It designates the page number and n lower order bits, that is n lower order bits designates the page offset. N lower order bits designates the page offset. So m minus 1 higher order bits indicates the page number, n bits indicates the page offset. This is the a basic method you have to address translation scheme. So this is the paging hardware. So every address is generated by the CPU. So here page number and offset. So logical address is generated page number plus offset. Physical address is generated by frame number plus offset. So a logical address is a page is stored into the page table. That page table, by using these frames, it can be stored into the physical memory. So this is the paging hardware. So see here, so this is a paging model of logical and physical memory. This is the paging model of logical and physical memory. Here, this is the logical memory. This is the page table, and this is the physical memory. So, logical memory, it will be stored fixed size frames, and physical memory, it will be stored by using the frame number. It will be stored the pages. So, what is a page? A process. What is a process is there? So what is the process size means? So a process size, it indicates the number of pages. What is the process size? The size of a process can be measured in number of pages. So page and enduku antunnamandi. So the size of process. So process is there, that is P1 process, P2 process and P3 process. So what is the process size means? The size of process can be measured in number of pages. The size of process can be measured in number of pages. That is nothing but page. For example, the process size is 3. That means the process can contain 3 number of pages. The process size is 5. That means a process can contain 5 pages. That the page. So here a logical memory contains a process that contains 4 pages. So from 0 to 1, 2, 3. And page table. So already I told you page table is nothing but it will store the index of that particular page numbers. This is the index 0, 1, 2, 3. So and 1, 4, 3, 7 are the pages. That is the frame numbers here. So previous diagrams in here. This is the page numbers here. It will be indicates, that is index, page numbers as an index, and here it will be as frames. That is the page table. So page numbers are the index and frames, that will be stored to the frame, and that particular location it will be stored into the physical memory. Same that here also. Here logical memory. So these pages are the index, that is the 0, 1, 2, 3, and here are the frames 1, 4, 3, 7. At frame 1, which page will be stored? Page 0. At frame 1, which page will be stored? Page 0. And see here, at frame 4, which page is stored? Page 1. So you see here, at frame 4, which page is stored? Page 1. At frame 3, which page is stored? Page 2. At frame 3, which page is stored? Page 2. At frame 7, which page is stored? Page 3. So here page 3. So this way we can store the CPU is generated some logic addresses. That addresses will be converted logical address and will be stored the pages as an page index. Page number as stored in a page index, and here it will be stored the frames for a physical address. For that frames number frame location, it will be stored the pages. So that is the concept of paging model of logical and physical memory. How to paging concept will between the logical and physical memory. This way we have to paging from logical memory to physical memory. And here another more example is there. So here paging here 32 byte memory and 4 byte pages, and 32 byte memory and 4 byte pages. So 4 byte pages is nothing but 1, 2, 3, 4 byte pages by using the logical memory. So these index values can be, these page number values can be stored as an index and particular frame numbers here, particular frame numbers. So see here, this diagram is visible or not? So by above concept only, here the data will be mapped, but it is a 4 byte pages. So one page is nothing but 4 bytes. So next one. So this is the free frames. So here when a process, so already we discussed when a process arises in the system, when a process arrives in the system to be executable. So in the question, when process arrives in the system is to be executable. Its size expressed in pages. So I already told you process is size is nothing but it expressed in number of pages. So each page of the process listen carefully, each page of the process needs one frame. So each page of the process needs one frame. So if the process requires, so if process requires n pages, so how many frames it requires? At least n frames must be available. Why? So each page of the process needs one frame. The process requires n pages. How many frames it will be required? N frames. Is it right or not? So process requires one page means, and also it equivalent to one frame it will be required. So when a process arrives into the execution, so the process size is examined. So what is the process size? So process size indicates in the terms of pages. So each page of the process needs, so here each page of the process needs one frame. One frame. So there are n number of frames, sorry, n number of pages. At least n frames must be available. దాని మీద ఎన్నన్నా ఉండొచ్చు, but at least n frames must be available in the memory. N frames must be available in the memory. So the first page of the process is loaded into one of allocated frames. So the first page of the process is loaded into one of the allocated frame, and frame number is put into the page table, and frame number is put into the page table for this process. So see, either before allocation this diagram, after allocation. So here free frame list is there. That is your vision, numbers and 14, 13, 18, 20, 15. You have to put whatever your numbers you want, that values you have to put here. So, and one process is arrived for execution. That process size is 4. That means how many pages it will require? 4 pages, right? That means process size is equal to number of pages. The process size is equal to 4. So that process will require how many number of pages? 4 pages. That is page 0, page 1, page 2, page 3. This is the free frame list. That is here from 13 to I will allocate it sequentially. That is 13, 14, 15, 16, 17, 18, 19, 20, 21. These are the free frames. So it is before allocation. And this one is after allocation. So here there are 4 number of pages, and this will be indicated as page number as an index. This is the page number, page 0, page 1, page 2, page 3. This will be indicated as index. So page 0, it will be stored 14. I already told you the first page of the process, that is page 0, is loaded into one of the allocation frame. And that frame number is put into the page table. So it's put into the page table. So see, page 0, the frame number is 14. So it also put into the page table. And page 1, the frame list value is 13. Next page 2, 18. Next page 3, 20. So here the frame list is there. That is physical memory. 13, 14, 15, 16, 17, 18, 19, 21. So here at 14th frame, which page is stored? Page 0. At 14th frame, which page is there? Page 0. So see here, at 14th frame, page 0. Next, at 13th frame, page 1. At 13th frame, page 1. At 18th frame, page 2. At 20th frame, page 2. Sorry, page 3. This way we have to allocate the frames. This is the before allocation, this is when the after allocation. Is it clear or not how to allocate the process into number of pages and by using the frames how it will be loaded into the physical memory? Is it clear or not? Is there is any doubts regarding free frames? So if there are n number of pages, at least how many frames it will be required? At least n frames must and should be available. So ikkada there are 1, 2, 3, 4, 5 frame listed there. 5 frames are there in the frame list. But at least 4 is there. So 15 free frame is it will be available at free frame list only. Is it clear? Is there is any doubts by using the free frame concept? Anyone can respond? Okay. Next, how the software hardware support. So paging, how hardware can support. So that is the implementation of page table we will see here. Implementation of page table. So operating system every operating system has its own methods. Every operating system has its own methods for storing page tables. So every operating system has its own methods for storing page tables. Here the hardware implementation of the page table can be done in several ways. The hardware implementation of the page table can be done in several ways. One of the simplest method for page table is, so it will dedicated as set of registers. So automatically the page table is kept in main memory. Here there are several ways that is implementation of that page table. So one is page table base register and page table length register. So page table base register and page table length register. So PTBR. So PTBR is nothing but page table base register. It points to the page table. So what is the page table base register? It points to the page table. So here the page table base register, the time required to access a user memory. So the time required to access a user memory location. So whereas page table length register, it indicates the size of page table, that is the page table base register, page table length register. So page table base register indicates or will point to the page table, whereas page table length register indicates the size of the page table. So by using this concept in this scheme, this implementation of page table, here we have to access the data or instructions. It will require two memory access, one for the page table and one for the data and instruction. So here a page table base register or page table length register, in this scheme we have to access data or instructions. It will require two memory addresses. It will require two memory addresses, one for page table and one for data instruction. So that is by using the PTBR and PTLR. So another scheme is there, that is TLB. That is nothing but TLB. So in this PTBR and PTLR, there is a one drawback, that is it will be two memory access there. So to overcome that, we are using a special fast lookup hardware. We are using a special fast lookup hardware cache. It is called as associative memory or translation look aside buffer. That is nothing but TLB. By using TLB, it is a high speed one. It is also called as associative memory. So here we overcome that problem, that is two memory access problem. We can solve by using the fast lookup hardware solution, that is TLB or associative memory. So TLB is nothing but translation look aside buffer. TLB is nothing but translation look aside buffer. So TLB contains two parts. One is key part, another one is value part. So here we will be calculate TLB miss and TLB hit. TLB miss and TLB hit. That is translation look aside buffer miss and translation look aside buffer hit. What is TLB miss? If you want to search one page, so if it is not in the TLB, if it is not in the TLB, then it is not, so that it is called as TLB miss. Then it is called as TLB miss. So if the page number is not in the TLB, the page number is not in the TLB, it is nothing but TLB miss. The page number is in the TLB, it is called as TLB hit. It is called as TLB hit. So that is the TLB miss and TLB hit. And hit ratio, how you can calculate the hit ratio? The percentage of time, that is a particular page number. The percentage of time that a particular page number is formed in the TLB is called the hit ratio. The percentage of time that is a particular page number is found in the TLB is called as hit ratio. So here this is the associative memory, that is TLB. The page and frame is there. So here what the translation look aside buffer. Translation look aside buffer. So translation look aside buffer is the concept. Here extra is there, that is here every address is generated by the CPU only. Here this is the logical address, this one is physical address. Logical address can be divided into page number and offset. Here physical address is generated by frame number and offset. So a page number, that is whatever the page number data is there, it is the index of that page table. Here page number and frame number is there. Here TLB. TLB is nothing but translation look aside buffer. If you want search some page number, if you want search some page number that is in TLB, means it will be go to the TLB hit. That TLB hit, it will be stored into that particular frame, is stored into the physical address. If you have to find out some page number that is not in TLB, it will be stored into the TLB miss. So again, so it will be TLB miss. So this is the TLB hit and TLB miss. Very, very important. Translation look aside buffer. What is TLB miss means? The page number is not in the TLB. automatically it will be go to the TLB miss. So if the page number is in the TLB, it will be go to the TLB hit, and that particular frames are stored into the physical memory. So this is the translation look aside buffer. So why we will use the translation look aside buffer means instead of two memory address accessing, we will use the TLB hardware solution. It is the high speed solution, and also here we will calculate the access time in very effective manner. So that is the translation look aside buffer. So in this way we have to calculate the effective access time. How you can calculate the effective access time is nothing but effective access time is equal to 1 plus a sigma into alpha plus 2 plus sigma into 1 minus alpha. So what is alpha here? Hit ratio. Already I told you. What is alpha is nothing but hit ratio. Hit ratio already told you. Percentage of times that a page number is found in TLB or associative memory. The percentage of times that a page number is found in associative registers or TLB, that is nothing but hit ratio. And what it indicates sigma. The next one is associative lookup. Associative lookup. So plus assume memory cycle is 1 microsecond. Assume microsecond is 1 microsecond. So this is not, so this formula we can use the effective access time. You have to calculate effective access time by using the TLB, translation look aside buffer. And next one is memory protection. Into a subtopic, memory protection. So what it will be memory protection? So protection means here there are, we can protect that values that protect the pages. So here we have to indicate that associating protection bit with each frame. That is, bit means valid bit or invalid bit. So we can attach by the page table valid or invalid. So by this way we can protect the data. See here, page table means extra you have to add one bit for frame. సో ఫ్రేమ్ నెంబర్కి ఎక్స్ట్రా ఒక బిట్ ఏం యాడ్ చేస్తున్నారండి, వన్ బిట్, దట్ ఈస్ వ్యాలిడ్ బిట్ ఆర్ ఇన్వాలిడ్ బిట్ యూ హ్యావ్ టు యాడ్. సో ఇన్ దిస్ memory protection, valid bit is nothing but associated page in the process logical address space. So valid bit indicates that, what it indicates that the associated page is in the process logical address space and is thus a legal page. Whereas what is invalid, it is not in the process logical address space. It is not in the process logical address space. In this way we can protecting the particular frame numbers. So see here, memory protection is implemented. Memory protection is implemented by associating protection bit with each frame. So associating with each frame. Here, see here, page 0, page 1, page 2, page 3, page 4, page 5. This is the logical memory. That page numbers as an index of the page table. Here frame numbers. So at 0 we will frame number 2 and 1, 3 allow store chestunna. So from 0 to 5 only the logical values is the logical memory pages. So that values only we have to stay V. V is nothing but valid. 6 and 7 are not there in logical memory. So that is nothing but invalid. So this way we have to protect that values, whether valid bit or not invalid bit. So is it clear? Valid bit is nothing but associated page. Associated page is the process logical address space. Is the process logical address space. So only 0 to 5 is there. 0 to 5 are valid. Remaining 6, 7 is not there. That is not in the process physical address space. So we have to kept invalid. The logical address space values is there. We have to put valid. If it is not there in logical address space, we have to put invalid. So at 0, that is page frame 2, we have to store page 0. At frame 3, we have to store page 1. At frame 4, we have to store page 2. In this way, we have to store entire frame structure into the entire pages into the physical memory. Is it clear?